Hello again, physics friends. We are progressing through our study of energy and the connection between energy and forces. And we'll recall that we've learned that a conservative force can be expressed as minus the gradient of the potential, where the potential will depend only on position. And that is, like I said, true for conservative forces. Okay. In one dimension, this problem simplifies because this del operator, this gradient operator, becomes a derivative with respect to the coordinate. And so if we consider our one dimension to be, let's say, in the x direction, we can talk about the force in the x direction as minus the derivative of the potential with respect to the coordinate x. And our potential can only depend on position, and there's only one position coordinate. Okay, so what we're going to see is we can learn something about the motion without even solving the equations of motion, just by looking at graphs of potential energy. So the potential energy graph can become a tool for us to study the motion of a system. So let's just draw out and talk through a potential energy graph. Okay. So I'll draw a graph that looks like this. It has minima, it has maxima, and so on. And let's call out a few specific locations here. Let's call out the location x1. Let's call out the location x2. And also let's call out the location x3 and x4. x3 is at the minimum there, and x4 is at the peak of this location, the local maximum. Okay. Now the first thing to recognize, right, is if you saw a particle moving in response to this potential, it would not move up, down, and left, right? This is one-dimensional motion. So the particle can only move, say, left or right on this x-axis. It can move faster and slower as it moves, or it can oscillate between 2 points, depending on the total energy, as we'll see, or it could sit at one fixed location if it's a stable point or an equilibrium point. But the particle does not follow along on this hill, on this hilly landscape, right? That would be two-dimensional motions, left, right, and up, down. So you have to imagine in your head a particle just moving left and right along this axis. Okay. But let's see what we can learn about the kinds of motion that this particle could make in the left-right direction. So let's look at position x1. At that position, the slope du dx is positive. In other words, if I look at a line tangent to the curve at that point, it has a positive slope. Okay. A positive slope, because the force is minus du dx, that tells us the force in the x direction is negative. There's a leftward force. Okay, so force points in the minus x hat direction. Okay. What that means then is if I put an object, a particle, at position x1, it would experience a force at that instant to the left. So if I put down by hand a particle of mass m right here and let it go, it would start moving to the left. Okay. How about at this other point, x2? Okay. Well, there at x2, we have a derivative that's negative, which means our force points in the positive x direction. Okay, so again, if I put my object at that location, it would experience a force that points to the right, a positive x force, away from the origin. For completeness, let's talk about these two cases, and at these two cases, my particle is at a local minima or local maxima. And specifically, at point x3, at both of these points, the first derivative, is 0. That's true at both x3 and x4. And so in both of these cases, the particle experiences no force. Okay, so we call this an equilibrium point. But as you might imagine, they're not the same kind of equilibrium, right? In one case, the potential u of x is concave up. In the other, it's concave down. So what do I mean by concave up and concave down? Well, by that I mean the second derivative, which gives me the curvature, is positive in the first case. So this is concave up. And that produces a stable equilibrium. Okay. In the second case, at point x4, the second derivative of the potential is negative. We think of that as concave down. That's an unstable equilibrium. Okay. What's the significance of an unstable versus a stable equilibrium? Well, imagine putting a mass at x3. It feels no force, okay, in the x direction, and it will just sit there. A particle that's at rest in the absence of a force will not move, right? That's Newton's first law. But what if you give it a little nudge and move it to the right a little bit? Well, if you move it to the right a little bit, now the particle is in a location that has a positive slope to u of x, which represents a negative force. So if you displace the particle to the right by a little bit, the force wants to bring it back to the left, back to equilibrium. And if you displace that particle to the left a little bit, the force is going to force it back to the equilibrium. And so you have this oscillatory motion. This is very much like a mass on a spring. So that's what we call a stable equilibrium. If you nudge the particle away from equilibrium, the particle will tend to return to equilibrium. Maybe it oscillates about equilibrium. But consider what happens in the case at point x4. If you put a particle down at x4 and you give it a little nudge to the right, now that particle will be in a place where the gradient is negative, and therefore the force, which is minus the gradient, is positive. So if you nudge the particle a little bit to the right, then the force makes it want to move even further away from equilibrium. So you have kind of a runaway process. And that creates what we call an unstable equilibrium. It's kind of like balancing a pencil on its tip. You might be able to get the pencil to balance exactly on its tip, but if you get a little push, it's going to tip over. It's not going to return to its tip. So we call that an unstable equilibrium. And having a mass in a stable equilibrium, that's kind of like a pendulum that hangs straight down. If you nudge the pendulum a little bit away from equilibrium, it will return to its equilibrium. One of the key ideas that we're going to focus on is, given any potential energy function near the local minima, the system will behave like a simple harmonic oscillator. In other words, there'll be a restoring force that's proportional to the displacement from equilibrium, and you'll get oscillations about equilibrium very much like that of a mass on a spring. And to see that play out, first we are going to talk literally about a mass on a spring and make sure that we understand how that works. And then we're going to talk about a pendulum, which is approximately like a mass on a spring. And then we'll extend that to any arbitrary potential energy function and talk about oscillations about stable equilibria. So that's where we're headed. And we will get there in future videos. But for now, take care and be well.